For decades, quantum computing has felt like this promise, right? Something fascinating, but always kind of living in labs or on whiteboards. Well, what happens when that promise finally becomes a reality? For us, 2025 was the year someone flipped the switch. It's the year quantum tech stopped being this thing of the future and actually started solving problems today. So what did that really look like?
Okay, just think about this for a second. What if we could discover brand new medicines in a matter of days instead of decades? Or what if we could untangle the most complicated supply chains on the entire planet, making everything faster, way more efficient? Or maybe build financial models so incredibly precise they could see through any market chaos. I mean, these sound like questions from a sci-fi movie, right? Well, they're not anymore.
Because you see, in 2025, we blew past a really critical threshold. We stepped into what people are calling the era of quantum utility. This is where these amazing machines started delivering real, tangible, honest-to-goodness commercial value.
All right, so let's get right into it. The real-world impact. We're not talking about some abstract calculations here. We are talking about major industries getting a serious competitive edge, like right now.
Check this out. 20%? Just on its own. It's just a number, right? But in the world of global logistics, oh, it's a full-blown revolution.
Yeah, that 20%, that's a massive cut in delivery times for companies like DHL. What they're doing is using quantum algorithms to look at literally millions of shipping routes all at once. They're optimizing everything, fuel, schedules, you name it. That package that shows up on your doorstep, it might have just gotten there faster because a quantum computer solved a puzzle that was just way too big for our normal computers.
Okay, you ready for another one? 80%. Now this number is shaking up one of the biggest industries on the planet, finance. And this one was all about teamwork. You've got JP Chase and Amazon teaming up to solve this monstrously complex problem, how to optimize gigantic investment portfolios. They came up with this system they call a decomposition pipeline, which basically just breaks the problem down into smaller bite-sized pieces. And get this, it shrank the problem size by 80%. That made it possible to run these calculations every single day, giving them a totally unprecedented edge in analyzing risk.
But look, the impact here goes way beyond just speed and money. Maybe the most profound thing quantum utility is doing is in an area that touches every single one of us, medicine. See, quantum computers are just perfectly built to model the very building blocks of life, right down at the molecular level.
So now you've got these huge pharmaceutical companies like Pfizer partnering up with IBM. They're using quantum computers to simulate how molecules interact with just incredible accuracy. This is speeding up the hunt for everything, from new antibiotics to super-targeted cancer treatments. It is a fundamental shift in how we discover medicine, a total game changer.
Okay, so that's the what. But the big question is, how? How is any of this even possible? What's the core technological leap that gives these machines such extraordinary power? And this right here, this illustrates the difference perfectly. So, in late 2025, Google gave its Willow quantum processor a really complex physics simulation to chew on. Willow finished the job in just over 2 hours. Now, the world's fastest supercomputer Frontier, it would have needed an estimated 3.2 years to do the same thing. That is a 13,000 times speed up. Just wow.
Look, this isn't just about being a little bit faster. This is what everyone in the industry calls verifiable quantum advantage. And it's not some theoretical benchmark, okay? It is solid proof that a quantum computer can solve a real, meaningful scientific problem at a speed that is, well, it's just plain impossible for any classical machine we have.
So we have this immense power, right? But there's always a catch. How in the world do you actually control a machine that operates on the incredibly fragile, delicate rules of quantum mechanics?
The single biggest challenge by far is errors, or what scientists call noise. A quantum state is unbelievably sensitive. I mean, the slightest little disturbance, a tiny vibration, a flicker in temperature, it can completely wreck a calculation. The best analogy I've heard is this. It's like trying to hear a single whisper in the middle of a sold-out rock concert. That whisper is your answer, and the concert is all the noise trying to drown it out.
So, how do you solve a problem like that? Well, as Michael Bierchuk, the CEO of Q-Control, puts it, the hero of this story isn't just the amazing hardware, it's the software. Specifically, it's the infrastructure software that's designed to manage all that chaos. And that brings us to something called quantum error correction, or QEC for short.
Okay, so if the quantum computer is that loud rock concert, then you can think of QEC software as these hyper-advanced, AI-powered, noise-canceling headphones. It is constantly monitoring the quantum state, it's anticipating errors from all that environmental noise, and it's applying corrections in real time. This active stabilization is the secret sauce. It's what makes the hardware reliable enough to actually give you the right answer, turning what was a fragile experiment into an incredibly useful tool.
Now, as you can imagine, this incredible new capability doesn't just exist in a vacuum. Of course not. It has kicked off a super high-stakes global race, and it has massive geopolitical and security implications.
Yeah, nations all over the world are pouring billions of dollars into developing their own quantum capabilities. We're seeing huge public investments. You've got Japan leading the pack with nearly $8 billion, and the United States right behind them at $7.7 billion. This is absolutely being treated as a matter of top-tier national strategic importance.
And here's the reason why the stakes are just so incredibly high. The very same power that can help us design new medicines, well, it can also be used to break the encryption that protects our entire digital world. We're talking everything, from your bank account to government communications to the secure messaging apps on your phone.
So how soon could this actually happen? Well, current studies are projecting there's up to a 34% chance that a quantum computer could crack our most common encryption standards, something like RSA 2048, in a single day, by the year 2034. That threat is not some far-off possibility anymore. It's getting pretty close.
This has naturally sparked a whole other race, the race to become quantum safe. And it all starts with just acknowledging the threat, really understanding that our data today isn't secure forever. The next step is to develop totally new encryption standards, known as post-quantum cryptography, or PQC. These are built on math problems so hard that even quantum computers can't solve them easily. And finally, it means building something called crypto agility into our systems, basically designing them so we can flip a switch to these new, stronger standards the second we need to.
So let's pull all this together. What does this moment really mean? Well, 2025 truly marked the beginning of a brand new chapter in the history of computation.
If there's one thing to take away from all this, it's this. Quantum computing is not a science experiment anymore. It's moved out of the lab and into the real world, and it's creating real value. For companies, for governments, for everyone. The central question has totally shifted. It's no longer if this technology will be useful. It's how are we going to use it to get a decisive advantage.
You know, we're standing at such a unique moment in history. For the very first time, we've built a fundamentally new way of processing information, a machine that actually thinks in the native language of the universe itself. It's almost like we've built a new kind of mind. And the only question left for us is, what are we going to ask it to think about first?